In problem 9.69, we have two objects. One of the objects is initially at rest, and then another object collides with that object and transfers kinetic energy to it. Actually, the amount of kinetic energy that the first object transfers to the second is 1/2 the original kinetic energy. And what's asked is, what is the ratio of the two masses that cause this type of interaction to occur? So what we have to do first is show a before picture where we have mass 1 traveling with velocity 1 before, and mass 2 is at rest. After, M1 has velocity 1 after, and M2 has velocity 2 after. Now what's given is that the kinetic energy of the second object after must be equal to 1/2 the kinetic energy of the first one before the collision takes place. Now our unknown is the mass of 1, the ratio of the mass 1 to mass 2. So that's what we're looking for. And our theory has several things we need to consider. First, of course, the momentum after, the momentum before should equal the momentum after. And since it's an elastic collision, the kinetic energy before ought to equal the kinetic energy after. And then since it's an elastic collision, we can use the relative velocity of approach and the velocity of separation equation to relate the velocities. So we know that the velocity of approach of mass 1 is just equal to v1 before, because mass 2 is not moving. But afterwards, the velocity of the first object with respect to the second object, that's the velocity of separation. There's how big it is, but we have to put a minus sign because it reverses direction. The velocity of approach is the negative of the velocity of separation. Now the solution is, well, the way I tackle the problem is to at least start off with the conservation of momentum equation. And that'll show all the variables, and then see how we can eliminate, in this particular case, eliminate those velocities in that equation so that we can find out how the masses are related. Well, if we start off with the conservation of momentum, then the mass of the first object times its velocity before must be equal to the mass of the first object times its velocity after plus the mass of the second object times its velocity after. And see, I've got these velocities that I have to eliminate, and so I'm going to have some of these other equations to help me do that. Now, the first thing I'm going to use is that the kinetic energy is conserved, which means that the kinetic energy I have before must be equal to the kinetic energy I have afterwards, okay? And I'm going to write that equation as follows, okay? The kinetic energy before is the kinetic energy of the first mass And that's got to equal the kinetic energy of the first afterwards plus the kinetic energy of the second one squared. So there is the conservation of kinetic energy. Now, our given tells us also that 1/2 the mass of the second one after, I'm sorry, 1/2 the mass of the second one times its velocity squared after. That's how much kinetic energy that it has after. That's got to equal 1/2 the kinetic energy of the first one. All right, so there's the kinetic energy that the second one has. So the first one has. So the second one has to have 1/2 of that. Well, I can use that to eliminate this term right here, and therefore I can get V1 before in terms of V1 after. And so let's do that. That it says that 1/2 M1 V1 before squared equals 1/2 M1 V1 after square plus 1/2 of V 1/2 MV square after, and that's equal to 1/2 M1 V1 before squared. 1/2 that kinetic energy right there. Now what I can do now is get is combine terms here for the velocity of 1 before, and when I do that, when I bring this 1/4 of this well, this is actually 1/2 of the kinetic energy before, and when I do the math right here, I get 1/4 of M1 V1 before squared equals 1/2 M1 V1 after squared. And if you solve this right here, V1 after squared, the m's cancel out, equals 1/2 of V1 before squared. And if I take the square root, then V1 after equals, I like, when I write the square root of 1/2, I like to write that as a square root of 2 over 2 times the velocity of 1 before. So that's going to allow me to eliminate or find the relationship between V1 after and V1 before. Now I'm going to use the, let's see, this is just the, I can get this out of the way right here, I think, just for the time being. Give me a little bit more room right here. So what I can do now is go to the elastic equation and see if I can't find some more relationships here that allow me to eliminate some of the variables. So I'm going to go to this equation right here and write that as V1 before equals V2 after minus V1 after. But what I'm looking for is find V2 after, so I can get it in terms of V1 before and V1 after, and I already know their relationships. So V2 after equals V1 before plus V1 after. Okay, now I can use that, all right? And so let's go on now and Let's go now continue with our elimination of the variables. I can go back to my original conservation of energy equation, which says that M1 V1 before equals, okay, M2, I'm sorry, M1 times V1 after, but we've already found that V1 after is the square root of 2 over 2 times V1 before. So that helps, okay? And then I've got to find, this term right here. Okay, I've got to use this information right here to finish out this term right here, which the term in the conservation of momentum, which is plus M2 times V2 after, but we just found that V2 after is V1 before plus V1 after. So there's a conservation of energy now using some of these relationships that we developed. And what we need to do right now is just expand this out. M1 V1 before equals M1 square root of 2 over 2 V1 before. Let's see. Okay, that's this term right here. I'm going to have to continue down the line. I don't want to eliminate all this over here yet. So that'd be plus M2 V1 before. That's this term right here. Plus M2 V1 after, like that. And if I just simply plug in, here it is right here. Here's the V1 after relationship that I wanted to keep right here. Then M1 V1 before equals M1 square root of 2 over 2 V1 before plus M2 V1 before. Okay, and then plus this last term, M2 times V1 before, V1 after, M2 V1 after, that term right there is square root of 2 over 2 V1 before, like that. All of these have the V1 before now, so I should be able to eliminate the velocities of 1 before. And then when I do that, I get M1 equals M1 square root of 2 over 2. I want to kind of isolate all this right here. Plus, okay, here is M2 times V1 before, which we've eliminated. Okay, and then plus this last term, M2 times the square root of 2 over 2, like that. So we just have to collect terms, and now collect the M1 terms. M1 times 1 plus the square root of 2 over 2. Oh, it should be a minus sign. I'll bring that on the other side of the equation. So that should be a minus, sorry. That should be a minus 1. Bring it on this side of the equation. And then collect the M2 terms. That equals M2 times 1 plus the square root of 2 over 2, like that. And then if I take M1 over M2, which I'm looking for, that equals 1 plus the square root of 2 over 2 divided by 1 minus the square root of 2 over 2, like that. And I'll